Hi everyone, good morning. This is Ming from Singularity Engineering, and today we're going to do a webinar on CVD simulations. Just a little quick background about Singularity Engineering. We are based in Oakland, California. We're a certified ANSYS channel partner. This means we provide the full suite of ANSYS solutions, from structural mechanics to fluid dynamics, electromagnetics, optical systems. ANSYS acquires and grows every year with new products, so we're looking forward to helping better serving our customers. We provide a full set of solutions. This includes software from ANSYS. We also provide training and services to supplement your needs. So if you have any interest in simulation, especially if you're based out of Northern California, please let us know. We'd be happy to get in touch and figure out if there's anything we can do to help you. So today we're going to look at CVD simulations. CVD, chemical vapor deposition, is a commonly used method to put very thin coatings on a wide range of materials. I'm going to pull up a simple model here that I've put together based on some standard ANSYS training geometry. We've made some differences to make this a little bit more realistic, but it's still a highly simplified model. All right, so here's the model. We have a chamber. On top, we have three nozzles that pumps gases in. The gas mixes in the top here, and then this is a shower heads option section where the flow diffuses through, and it's going to eventually deposit the material on the inside here, on the top surface here. So the surface probably should be a little bit lower. We have a wide range of customers, companies that make these systems are often a big fan of simulation because these systems are fairly complicated. You have multiple chemicals flowing in, and you want to have as uniform of a deposition as possible. So you want the flow to drop down evenly through the shower head onto the deposition surface. The surface is spinning, which is a way to try to have a more uniform deposition, but also changes the flow patterns. You may adjust the temperature on this because the chemical reactions that we look at are highly sensitive to the temperature. And you may want to have a transient pulsing scheme where different chemicals and different reactions will occur to whether to deposit different layers of chemicals and maybe cleanse some of the materials from the system as well. So looking at these type of CVD systems, as I said, they're used to create very thin coating, whether it's or it can be used to create powders and fibers. Um, the simulations themselves can be complex, so obviously geometry can be very complicated with the very small channels in the shower heads. We want very uniform diffusion down to the wafer surface. There's surface chemistry going on that we can simulate later on. And there's also desorption of byproducts from the surface. So when the chemical reaction happens, some of the materials that's produced we don't want. So we want to whisk it away with different types of chemicals. And finally, we want everything to kind of drain out the back, anything that you don't want in the simulation. The temperatures can be very high in these models, so controlling the temperature is important. Making sure the right temperature gradient develops inside of our model is important. You may adjust the pressure, the flow rate, the timing, maybe sometimes even put in a plasma field or a field to try to increase the mixing and the deposition rate. So with all of those controls, it's no wonder that these simulations becomes very popular. It's much easier to control all of these things in simulation rather than trying to build a lot of different devices and running various conditions to see what produces a smoother deposition. So let's go ahead and take a look at how we set up this model. Usually, the first thing we do is we set up a flow model. A flow model can include all of these little holes for the shower head, but oftentimes to start out with, it's probably better to model that section as a porous media. So I'm going to split the body along this face here. and that cuts away that section, and then we'll do the same thing with the split down here. So once we get rid of all of the small holes that's representing the shower head, I can then create a volume and make it a porous volume. The volume will then represent all of the shower heads. We'll put in a specific porosity information in that area so that the flow is only allowed to go in the z-axis, and we have the right pressure drop, pressure flow rate drop through that area. So I'm going to do Control-C, Control-V. This creates a surface. We're going to pull this surface up to the top. Okay, so this will be my porous region. Let's rename this. And we want the mesh to match up. We don't want any non-conformal meshing going on here. So the way we do that in space claim is we do the share topology option. We can also do it in the workbench section. So you just click on share. It's going to go through my entire model, figure out that there are two surfaces that could be shared. I hit OK. Those purple lines indicates these interfaces are shared now. Now we can go ahead and do our analysis. So I'm going to just save this. CVD, we'll call this the CVD workshop document. Okay, we can go into Workbench to set up the model. You can also go into Fluent directly. Over the last few years, ANSYS has deployed ANSYS Fluent Meshing, which allows you to do all these simulations directly in Fluent. But I'm pretty used to Workbench, so we're going to go through that example in this case. Okay, so we have all of our different tools available in Workbench. On the left-hand side here, I'm going to drag a fluid flow fluent option in, and we can go into the meshing and start preparing our simulation. So this is ANSYS Workbench Meshing. It's a common mesher used by ANSYS Mechanical and all the ANSYS CFD tools, and maybe some of the other tools as well. So if you're familiar with one use of it, you should be pretty comfortable with this tool. If you're familiar with any of the ANSYS Workbench simulation tools. So we can just generate a coarse mesh here. It's probably a little bit too coarse. I want to keep this small so we can run some real simulations, but at the same time, if it's too coarse, then we run the risk of really having poor quality results. So the area of interest here is a porous zone. Right now, we just have one element through the thickness. That's not really desirable. So I'm going to change this from the regular method to multi-zone, and we're going to put in a sweep element size. So these things are, maybe 5 millimeters wide. So let's do 2 millimeters. So that looks like it'll put about 3 elements through the thickness of the porous zone. We can also put in inflation layers in all 3 sections. So the reason I went with multi-zone is because multi-zone allows us to specify inflation layers very easily. And we want inflation layers pretty much on the entire outside surface, as well as the inside. So anywhere where there's a wall, let's extend to limit, we want inflation layers. Let's cut it open. Oh, probably should hit apply here. Now I can't really see inside properly because the mesh is blocking it, but if I click on that, it fixes that issue. So we got all the outside done. Let's also do the inside here. So I'm holding down Control to select all of the surfaces. Right, so that looks like all of the surfaces are selected. I'm going to use a standard smooth transition, but you can certainly adjust this to first layer thickness or total thickness for the inflation. Okay, the inflation layer has been generated. You can see that it kind of goes through the porous region. Got that surface. This mesh doesn't look great over here, I have to say. I think this surface turn was a little bit too spiky. Yeah, somehow that does not look all that great. Yeah, I think we probably should refine the mesh over here to get a better better solution. So that we may have some convergence issues in this. We can check the mesh quality. Mesh metric, element quality. Oh, okay, so element quality is not great. The least quality is 0.02, but it's not horrible, so I think it's probably okay. We're going to push ahead with the simulation. Hopefully it works out okay. The next step we want to do is make sure we assign our boundary conditions. So we need to flag the surfaces and as well as the volumes in the analysis. So this will be my top volume. This will be the porous volume. And then on the bottom, just for completeness, volume here. So that's the volumes. This allows us to specify porosity behavior in the porous region here. Now we want to specify the inlets here, inlet and outlet boundary conditions. So let's create this will be an inlet. In this one, we'll have H2 pumped in another port. We'll have game 3. And then in this port, ash. Okay. Let's double check, make sure we got all of them set up here. We need an outlet. So let's create I'm just right clicking and you can see you can press N for that as well. So this will be the outlet. And let's split it open. So I can use a shortcut N here and automatically allows me to specify a name selection. So this will be my deposition surface. And then this whole disk is actually spinning, so I need to select the rest of it and create a name selection. Spinning wall. Okay. All right. So that's it. That's a model with all of the required boundary conditions defined. Now we can go back to our Workbench project page. We'll do an update and then bring it into simulation. So we're going to run this on 5 cores. We'll try to run a few simulations during this webinar. Okay, it's coming up on my other screen. Once it's done, I'll try to drag it over here. There we go. Okay, the nice thing about the simulation is that ANSYS has already figured out where the inlet and outlets are. So we typically just work our way down here. So under general, we're pressure-based, steady state, absolute velocity formulation. We want to adjust solver defaults based on the setup, and then we have a gravity of 9.8 meters per second squared in the z direction. Okay, so next we got models. Multi-phase is off. Energy needs to be turned on. We do want to calculate the temperature distribution because the chemical reactions are sensitive to temperature. Radiation heat exchanger is off. Species is turned on here. And for now, we're only going to do a regular kind of simulation with a flow, but we'll add in chemical reactions a little bit later in our next section here. Everything else is set as normal here. So we have some fluids and mixture. You can see the mixture involves water vapor, oxygen, and nitrogen. So that's not the materials we want in our simulation. So we're gonna right. So this is not. So we want to add in the right materials into the fluid. So we're gonna change the air, and we'll open up the Fluent database for fluids. Switch to chemical formula names. So I think the first one we want is ash3. Then we want to have in a basic flow mixing kind of simulation. I'm gonna find GAM3, and then we want hydrogen. So those are the three materials we want. We don't really need air. Oh no, cancel. Okay. All right, so we have our right materials. Get rid of air because that's not going to be a part of the simulation. And for the mixing template, the materials will actually be these three. Because we add this one at a time, and then remove. And we want to make H2 the last species. So this will be kind of the catch-all. We specify the mass fraction and the volume of game and ash, and whatever's left over will be hydrogen. I'm going to go with ideal gas, mixing law, thermal conductivity, mixing law, viscosity. Let's do a mass-weighted mixing law. Mass diffusivity, we'll leave that be here. So that's then going to be our simulation. We'll have this mixture in the analysis. Let's double check here. So, yep, 3 species all set up here. So now we want to look at the cell zones. So you can see we're just working our way down here. The bottom, right? Everything is using a mixture template. We have nothing is rotating in this case. But the porous media, we do, right now we just have a block representing a shower head. In reality, the shower heads will prevent any flow in the X and the Y direction. It only allows flow in the Z direction. And there's a pressure drop because we're squeezing flow through very small holes. So we definitely want to turn on the porous media in this. And oops, where did it go? Oh, here we go. So this is our porous media materials mixture template. Reference frame is the same, but now we can specify the direction. So we want to make sure the direction 1 is in the z-axis. This makes it easy. Now we just know that we want flow to go in direction 1. We don't want them to go in any of the other directions, right? So we specified the second direction, and the third direction is implied, or it's calculated for us. We can specify here the viscous resistance, inertial resistance, power law, fluid porosity, etc. So if you haven't done so before, it's very helpful to look at the help here for porous zone. And there's a section for inputting porous zone. You can look at the user inputs for there's power law, viscous resistance. So if you want to look at, for example, the viscous resistance and inertial resistance formula coefficients, we can click on that and get the equations. down here, and ANSYS has some guidance for you to deriving porous media input based on velocity and pressure loss. So you can set up a simulation of, say, a unit cell of your very large shower head model. You can run a series of simulations with known velocities and look at the pressure drop, or vice versa. You get a curve, and based on that curve, you can then go through this process of figuring out what the coefficients are. So I did that for some basic models here. I think what I did was I just made the X and Y direction, the direction 2, direction 3, 100 times larger in terms of resistance. And that will prevent flow from going in those directions. Similarly, for inertial resistance, let me actually open up my old model here and see what we use for that. So I used the value of 30,000. So again, I made the other two values about 100 times larger to reduce the likelihood of flow going in other directions. So setting up the zones now, the next step is the boundary conditions. And really we're very interested in the inlets of the boundary conditions. What you notice here is I have 3 boundaries, so each of the pipes will have kind of one chemical come in. It'll mix inside the top chamber and kind of diffuse down into the bottom deposition chamber through the shower head. By default, these are all set to be velocity inlets. Most of the folks working in this industry tend to do volumetric flow rates. We don't have that option, but we do have mass flow rate, which is pretty much the same. You just gotta multiply the volumetric flow rate by the density, and then you get mass flow rate. So here we have inlet of ash, and a lot of times it's given as schemes, CCM units, but we can convert that to mass flow rate as well. So here, let's put in the momentum. Mass flow rate for ash is just a little bit here, and it's all going to be this species. Game here. And this will also be normal to the boundary, and the momentum value, the mass flow rate, is that, and this will be all mass fraction of game. Finally, H2, let me see what we want normal to the boundary, and H2 is only a little bit of mass flow. Everything else is at room temperature here, and species is 0, so okay. Internal, these are the interior zones where we need to connect one physics to another, for example, across the porous domain. Outlet is just gauge pressure, and 0, 0 means that the outlet will be all hydrogen. So if there's any reverse flows, hydrogen will flow inside. And next we want to look at the walls. So the deposition surface is going to be heated very heavily. So it's also a moving wall. So this surface will be rotating at 80 radians per second around the z-axis. Temperature, we're going to do 1,000 degrees. So a lot of times people would want to do actual thermal models of this to see what the actual temperature is, because chemical reactions can be so sensitive to this. But in this case, we'll keep the simulation simple and just have a standard temperature defined, a fixed temperature defined. Spinning wall here. This is also a moving wall. and it's going to be rotating in the z-axis at 80 radians per second. Temperature will have 0 heat flux, and that's it. So you can see setting up these simulations are pretty straightforward. We want to adjust. We can adjust the operating condition. So this will be at a little bit lower pressure, 10,000 pascals. We have gravity defined. So for solution, we can let's go to 20 iterations to make sure we get a good initial condition. Okay, now that we have all of the boundary conditions set up, let's go ahead and initialize our simulation. And we'll run a few iterations and take a look at the results. Okay, so I don't think I'll let this run to completion in the interest of time. So I'm going to stop the simulation here. And we can take a look at some of the results, preliminary results, so that these are not the final results, but let's take a plane, and we can, so we're down in the results section now. Let's create a new contour on the plane, and we can look at some of the species. Okay. So this is a diffusion of game onto the through the volume. We can look at Ash3 and H2. So this is all the mass fraction telling you the relative amount of different material being deposited on the surface. It looks like depending on where the nozzle is, we have different results. We can also look at things like velocity. ANSYS has a couple of options for post-processing. I showed you the fluent post-processing, which is pretty good. It can typically do all of the things that you need to do for these models. A more full-powered post-processor is available here in CFD Post. It can create some very nice images for presentations and such. So I'll show you what we can do here as well. So we got 3 inlets. So one of the things we can do is we can do a volumetric rendering for the mass fraction of species 0. This would be the hydrogen species. We can look at species 1 to see where the concentration is over here. And you can compare the different types of visualization. We can also create streamlines let's say from the 3 inlets, we'll do 50 to 60. So we should get about 20 lines from each. And you can see how they kind of all go in there and mix. And depending on the mass flow rate, because I have the same inlet diameter, we have different velocities. Some of it goes up to 70 meters per second, others are almost stagnant. That causes a difference in the behavior. You can also see that when we go through the pore zone, right, the flow is mostly vertical. There's some turning. We can reduce that by increasing the amount of resistance in the X and Y direction, but this kind of shows you the way that porosity region works. Also do a quick animation of the streamline here to see how the flow is. We can maybe color things differently, have multiple streamlines and such all animated together. So lots of options for visualizing the flow, but the point here is that we're able to see the mixing, and we can look at the surface on the, let's turn this off. We can look at the deposition surface and look at what the concentration is for each of the variables of interest. So let's do a local concentration plot. So it looks pretty uniform here. Species 1 and species 2. Okay. So it shows you there's probably could use some more refined mesh to capture this behavior better, but we can, and obviously the simulation is not finished converging, so we could definitely run more analysis with denser mesh, but this is kind of the basics of what you can do to ensure you have a even diffusion of chemicals down onto the deposition surface. Okay, let's close that off. So the next step we can do is we can, I'm going to duplicate this, and then we can add in the surface reaction. So right now we have everything falling onto the surface, but nothing is actually happening on the surface itself. So we're going to call this surface reaction. And let's take a look at the settings here. So we'll set this up again. We're going to start from our current model, which has all of the flows, but we're going to add a few more species and some more, and the actual reaction part of it. So let's go ahead and take a look. Okay, let's try to drag it over here. It's almost done loading it up. Okay, so we have our model here that we did previously. It's going to be much the same, except we're going to add in the surface reaction. So the first thing we want to do is bring in some more materials. Right now I have 3 mixtures, 3 species in one mixture all sprayed in here. These are our reactants. We also have a product, so some of these will generate products, and product will be a mixture of the actual deposition and also other gases and such. And we also need some site species. So basically, we need to add in a few more materials. And luckily, there is a option to import a material in into Fluent. So I have you can export it as well, but I've imported this. I've created a library of CVD materials for this particular project. For example, there's a deposition, and then we have the fluid materials and the solid materials. So on the fluid side, we have ash, but we want to add in the solid. Oh, unselect that. So arsenic and gallium. These are the deposition material, and also site species for the deposition material. We also want to include a methyl radical. This is a product that we'll need that gets produced during the reaction. So when we copy all of that in, and you can see my material lists have increased to this. Then we go to mixtures, and this is our gallium deposition with mixture species. I'll set all this up instead of copying it over. Actually, maybe we should copy it over. Yeah, we can always let's copy. Okay. Oh no. Okay, I think I tried to copy it into the. Here we go. Let's try that again. Oh, I think I may have overridden the material library. So that's fine. We'll set up the actual reaction itself. I wanted to copy it in so we can kind of compare the two, but as it is, this is fine. So we have it's essentially the same setup. We have a few more species here. Specifically, we had the reactants before. Now we need to put in all the products. So under species transport now, we're going to turn on our reactions, and this will be all wall surface reactions. The reactions doesn't take place in the chamber itself. It only happens when the chemicals hit the site species on the deposition surface. So these are going to be wall surface reactions. There will be mass deposition sources, not heat of surface reaction sources, and we have full multi-component diffusion to capture that more accurately. So let's take a look at the mixture template here. We have mixture species. Right now we have all of these. We want to add in my methyl radical to this. Okay, so you can see. Okay, I have to hit apply, I think, because otherwise it won't let me. So some reason the wall surface, none of this got. I think I need to apply here to ensure that it takes. Now when I go back here, see I can now, because there's now this. Let me move this. I can't really see it, but there's a surface reaction defined. I can start specifying site species and solids. So these are my site species, and these are my solids. Okay, and we want to make H2 the last species. That's again our limiting material. So whatever's not in the leftover mass fraction will be all hydrogen. So we're good here. The reaction will be finite rate reaction. So let's I will define this, but let me find the numbers I need in my already set up simulation here. Okay, here we go. So there's going to be a total of two reactions. We're going to be depositing gallium and arsenic onto the wafer here. So the first one is going to be my gallium deposition reaction. This will be a wall surface reaction. We'll have 2 reactants and 3 products. So you can see it's very easy to set up here. When I do that, it sometimes pops to my other screen, but that's okay. So the first one, the gallium deposition, will be ash, and our gallium site species. I'll show you the material properties later on. You can also just get it from the ANSYS training material. There's a tutorial attached to Fluent that has this deposition simulation. So I just took some numbers from that to make this simulation a little bit easier. So this should be 1.5. Right, so we're looking at ash. Will react with gallium site, and it's going to deposit some gallium and it'll create a more an arsenic site species, and then it'll actually also create some hydrogen along with it. So this is looks like 1,000,000 exponential factor. Activation energy 0, so it's just gonna activate as soon as it reaches that, and then temperature exponent is 0.5. So this shows you how to set up a finite rate chemistry. These need to be double checked. Obviously, you want to make sure you have the right reaction rate defined. Also, heat generation and things like that should be included. The second reaction is also a wall surface-based reaction, and this will be my arsenic deposition. Same as before, this basic 2 equation, two reactants and 3 products. Here we have game 3, and it's going to react with my arsenic site species, and it'll produce some arsenic being deposited on. We'll have a gallium site created, and then some CH3 is also created here, and actually apparently there will be 3 of these. So let's put this information in again. It's going to be readily activated. 0.5 is the temperature exponent. So it's complaining about some mass imbalance. Definitely want to check to make sure that all the masses make sense. And but we can carry on with the simulation as it is. And finally, we want to adjust our reaction mechanisms. So these two number of sites, we're going to say they're just there should be wall and surface reactions. One site. Oh, site density is 1e minus 8. So there's total number of site is 1. We have a density of the site, and then if we define it is 2 species. We have gallium and arsenite, and I think it's 70-30. 0.3. The total number of sites. So initially there's more gallium sites than arsenic, but as the deposition happens, things will probably even up. Okay, so we've changed the first 3 of the inputs for the mixture property. Ideal gas law for density and mixing law, everything else gets carried over from the previous setup. So this is it. We have everything we needed to be set up here. On the species side, we've filled in the materials. The cell zones, the inlet and outlets, and the porous media doesn't really change. But what we do change is that now on deposition surface, we have some sites for deposition. So if we go to species, you can see we can specify the reaction, and we'll say that, yeah, there's reaction on the surface, and it's all fully covered by these sites. So again, that's all it takes to set up a simulation that involves surface chemistry. We can take a look at some of the materials we created here. So arsenic is just another fluid material with it's a gas, CP constant value kinetic theory for the thermal conductivity and viscosity. And then we have some basic material properties. I'm not sure about these materials. Again, I grabbed it from the ANSYS training material, but definitely worthwhile researching some literature, understanding what your actual materials are. The site species is the same as well. It's just a regular fluid with a density, specific heat, thermal conductivity, and all of the rest of the information you'd want. Okay. So let's go ahead and solve this analysis now. and we go ahead and run a few iterations. Again, I don't think I would let it run to convergence. It'll take too long for us to watch the convergence plot drop, but we should get we'll get some results to take a quick look at once we get once the simulation progresses a little bit. You can see initially there's no CH3. That's this blue line suddenly popped up after the first iteration because the reaction is happening. There is reaction happening. We want to track to see the amount of CH3 produced. Just want to wait until the reverse flow kind of dies down a little bit more before we pause the simulation and take a look at the results. Maybe we'll wait till about 30 iterations, just like we did before. It's certainly not enough for a converged result, but hopefully it has enough stability for us to take a look at something without it looking totally wrong. Okay, let me stop this solver here. Okay, so the benefit of turning on surface chemistry is now we can plot the contours on the deposition surface, and under species, there's option of looking at the deposition rate of gallium. Oh, there you go. So that's the deposition of gallium, and then we can look at the deposition rate of arsenic. Looks very similar, and this is obviously due to the fact that we have very poor uniformity in the shower head region. So you can see how important it is to have good good performance on your shower head and the flow region, because if the flow is wrong, then it's obviously not, the results are not great. Do we have a surface already defined? No. Okay, let's put in a plane. Okay, that's a plane we put on, and we can look at maybe the temperature plot on that plane. Let's create a contour of the temperature on the newly created plane. Okay, so remember we have 1,000 degrees here. You can see it quickly cools off, and when the cold air and chemicals hits it, it cools down quickly. And this is a case where having inflation layer near the deposition region is really important, because we want to have the right temperature gradient. Again, you can put a heat source on the bottom too, and you can see how well you can control the temperature. Temperature, it does end up being quite useful. We can still look at the species. Let's see, there's a new species, a mass fraction of CH3, and you can see this is being created based on the reactions that's happening. There's more reaction over here, so we have more CH3 probably produced over here and less reaction over here, so you can see it's more green. It eventually gets washed away down to the bottom, hopefully, and it leaves the domain. So that shows you how we can set up a surface chemistry model, right? We need to put in the site species, the deposition species, in addition to all of our existing chemicals. So which, the products are, we have to put that in as well, since we have chemical reactions. Then we need to specify under the mixture material the species that's involved, including the surface reaction species. the reaction itself, as well as reaction mechanism. Then finally, we have to find the location where deposition is happening and assign the, assign the mechanism and the distribution of the sites to that location. So that's how we go about setting up a deposition. The last thing I wanted to show was, we've looked at so far, our simulation can potentially adjust different amounts of flow into the system. We can adjust the temperature, rotational velocity. We can even adjust some of the chemistry information. But the last thing is oftentimes people want to operate these things not as a continuous deposition, but in bursts. You may want to put different deposition of different material in different multiple layers, in which case you want to put chemical in, flush out the residue, put more chemical in. So transient and timing becomes important. So the last one we want to do is look at a timing simulation or transient analysis. So this one, I'll move it to over here, and we'll do this one called, it's going to be called my transient simulation. Okay, looks like we can move it over now. Okay, so here's our steady state simulation. Let's make this analysis transient. So go to the General tab here, and there's a button that says Transient. Click on that. You can see a bunch of things gets updated. This is a very useful tool to adjust solver default based on setup. ANSYS developer tries to do their best to have the right settings defined over here. So it's good to have that turned on, so you don't have to remember what under relaxation factor to adjust to make the simulation more realistic. Everything else is essentially the same. The only thing we want to adjust here is my flow rates. So rather than having a continuous amount of gas flowing in, like I have here, I want this to be a transient, time varying gas flow rate. So you can create an expression, UDF or such, but the easiest way to do this is just put in a profile. A profile is a text file that looks something like this. It's very simple. If you search for profiles in the ANSYS help, you'll find an example that looks something like this. Basically, the profile will be called transient profile. It's a transient profile, so ANSYS knows that one of the sets of data will be the time data. And each of the time data will have a corresponding value for H2, ASH3, and game3. So this means that at 0, so it's always linearly interpolating from 0 to 0.15. This first value will be the mass flow mass flow rate for each one of these materials. And then, a hundredth of a second later, it's the next column, and then 150 milliseconds later, it'll be the column after. So what we're doing here is we're pulsing game a couple times. In the middle, we're putting some ash in, and then we're doing game again, and then through that whole thing, hydrogen is being flowed normally. So let's see what happens when we load this up. So we're going to read from the CVD that we have a transient profile here. Super small file, but you can see it reads in all of these variables. So now instead of having to deal with a static or a constant value for mass flow rate, I can just say this will use the transient profile for ASH3. Everything else is the same, so that this is ASH3. we're going to use the transient profile for game 3, species, game 3, double checking to make sure that when I updated the boundary condition, nothing accidentally got changed here. H2, 0, 0. That's it. So once we have the simulation set up with the transients, now we have time varying mass flow rates. You can also look at walls, so there's lots of things you can potentially use profiles on. You can potentially have a profile for changing of the rotational speed, surface roughness. So almost any of this stuff can be adjusted as a function of time. So let's go ahead and, before we do that, we typically want to save some additional results. Automatic save every step just means it's not going to save anything, so we can, sometimes I do 10, sometimes I do 5 steps, so I'll save a result every 5 steps. Right, okay. You can also monitor additional results, so instead of, you can do a report plot, add some additional plots so that during the simulation you can monitor it. But that's all we need to do. So standard initialization, and typically a typical time step is like 0.01, 0.001. So we can run 100, 1,000 time steps. This whole thing doesn't last very long, so we can go back to the amount of time it's going to take to run the whole simulation, real physically defined transient simulation time. I guess we want to look at our table here. So the maximum is 1 second. So we really want to run a second of the simulation. And this is what happens during a transient analysis. You see that there's outer loops, and so for each time step, ANSYS will iterate a number of times here. It looks like about 20 iterations to come to a convergence. Once it hits that time step, it'll move forward, and you can see the convergence improves a little bit with each step. So we're marching forward in milliseconds to see how the flow will evolve as we move forward. We're running pretty short on time, so I'm going to stop at the end of the time step, and we can open up an existing simulation for the transient. Transient analysis tend to be orders of magnitude longer to run than steady state simulation, so you definitely want to use transient simulation sparingly. The other thing is that we often use a steady state result to initialize our transient simulation. That gives better convergence, and you can save a lot of times in terms of getting rid of the initial maybe transient flow behavior. So here I have CFD post. We can color it with let's say the mass fraction of species 0, and we can just do a time step animation. You can see how the different materials gets built up over time. I think one of my other planes, let's delete this one. You can see another mass fraction of a different species. Just a little bit of change down there. And let's check this out. Okay, so it shows you that initially it was blue, and then we start feeding it in, and then it should turn, it should stop again. So this is a type of simulation you can do where you pulse on and off different inlets. You can control the mass flow rate into your system. You can specify the time that it goes in. You can specify the temperature of all the walls. You can specify you can try out different types of chemical reaction rates. And at the end of the day, you get production of deposition, and you can look at the thickness and the rate of deposition at different locations. So we've kind of run out of time. Hopefully that was informative to all of you. Thank you for your attention. Again, we're Singularity Engineering. If you're interested in chatting with us about this type of application, feel free to reach out to us at www.singularityeng.com. If you like the presentation like this, please do subscribe to our channel. We'll try to put more good resources out there over time.